Newton's method. So, say you wanted to solve some crazy equation like this. All right? You basically don't have the tools to do it. If it was a quadratic, you'd pull everything to one side and factor. You could try factoring this. That's going to be not a lot of fun. Okay? You could try some polynomial division stuff and factor it, but it might not be factorable. Anyway, so you can use what's called Newton's method. Now I'm going to show you how to use this. This is essentially what Desmos does. It uses Newton's method. It uses an algorithm to do this.
Basically Desmos?
Yeah, you're acting like Desmos right now. Okay, so this is what Newton's method does. Number one, you make initial guess. All right. We're going to call it x1. We use it to solve x-intercepts. That's the real thing, is what we're going to do. Okay, so I just make my guess x1. I'm trying to figure out the x-intercept of this graph. This graph is not the equation I wrote up there. I'm just making that up. And then you find the tangent line at that point. Okay, so the initial guess x1. Now I'm going to show you this visually. All right, so you find the tangent line. I guess I should use the ruler. Well, I picked a poor initial guess. Sorry. There. You can just alter your graph. Okay. So there's the tangent line at x1. The red line there. All right. Then you take the y-intercept, which we're calling x2, of that tangent line. And you go down to the graph. And you find a tangent line at that point. So at this point right here. It doesn't really matter for now. I'm just showing you the visual of how this works. I care that you understand the visual, actually. That's what I care about more. Because the other part you're going to see in a sec is just a formula that you just plug numbers in. All right? So you get your first guess. You just guess, okay, this is the x-intercept I want. I just pick a number that is relatively close. I'll show you how you can figure that out later on. You go up to the graph, you do the tangent line at that point. You take the x-intercept of that point, and you go down to the graph and you find the tangent line there. And you take this x-intercept, you go up till you hit this graph, and you do the tangent line at that point. That's x is 3. So, whoops.
this going forever?
No, because you'll see what happens. This point, this is x3. Then you do the tangent line at x3. And what do you get? Where's the x-intercept of this tangent line? It's at the x-intercept of the original graph. Okay? Okay? So my goal was to find the x-intercept. So I pick a point on the graph. I do a tangent line. I take the x-intercept of that and I put it into the original, and I do a tangent line again. I take the x-intercept of that one, I put it into the original, I do the tangent line, and eventually, if you do it enough times, you get to the x-intercept.
Enough times. How many times?
Well, in reality, you'd have to do it. Well, we're gonna do one. We're gonna do one. You'll see. All right. It's usually 3 times, but it's a formula that you follow. It's not that hard. This is what Desmos does. This is what you had to do 400 years ago to find x-intercepts and to solve complex equations. This is the stuff you had to do. All right. So okay. That's xn. N plus 1? Sorry. There, is that better? Plus 1. All right. So we'll do this with one that we know what the answer is. This is the formula. All right.
We're literally doing ice tables.
Yeah.
It's not an ice table.
You wouldn't know.
Yeah.
You can just stay out of the
You don't understand.
My degree is in chemistry.
You didn't take chemistry. Why didn't you take it?
I don't need it though. Because it's
I don't
boring.
need it.
No offense, Colton.
I want to keep my memories
All right. So we know how to solve this equation, but we're going to see how close we can get using Newton's method. Okay. So we're going to find the zero, i.e. the x-intercept of x squared minus 2 on the interval 0, 2. So usually I will give you an interval, but if I don't, you could use intermediate value theorem to find out a decent approximation, because the intermediate value theorem, if you remember from the very first chapter, if you tested x is equal to 0, you're going to get a negative number, right? If I put 0 in here, do I get a negative number? Yeah. If I put, or sorry, let's say, yeah, and then I test 1 right in the middle. If I put 1 in here, do I get a negative number? Yeah. Okay. So then if I test 2, I'm going to get a positive number. So it's somewhere between 1 and 2. Okay. I'm just going to use 1 as the initial guess because it's in the middle. All right. But you could use 1.5 if you wanted, but I'm going to choose 1 because it's a nice number. All right.
You just solve
So-
any equation. Like that.
Essentially, you could solve any equation as long as it's continuous. I know.
So if you were to like.
That doesn't matter though, right? It's just you want to be close, because if you're positive and it's negative at 1, you know it's between 1 and 1.5 is the answer, right? Okay. Yeah. Okay, so you put 1 into the original. What's 1 minus 2? Negative 1. Okay. What's the derivative of this function? 2x, right? If I put 1 into the derivative, what do I get? 2. All right. Then you put, this is just to collect the information. This is the Newton's method formula. X to the n, this is our initial guess, all right, which we're saying is 1. So I go 1 minus f of 1, which is negative 1, over 2, f prime. What does that give me? What's 1 minus negative a half? 3 over 2. I'm going to use the decimal because we actually want the decimals in this case. So 1.5. All right. That is, if you're on this thing, that's this line. Okay. All right. It's actually this point. Now I'm going to use that point to do it again. So you go. Yeah. That was just a visual representation. This is the actual doing of it. So you go f of 1.5. I'm just going to give you the answers, okay? You put it into the original, you're going to get 0.25. You put 1.5 into the derivative, you're going to get 3.
So that second, like the.
That point?
No, the one before it.
This one?
Is that supposed to be F prime?
Yeah, that's f prime. Sorry. Thank you.
Oh.
Then x to the n is your first point, which is 1.5, minus f of 1.5, which is 0.25, divided by f prime of that number, which is 3. And if you put that in your calculator, you're going to get 1.4167.
How do we know when we get to the
You'll see in a sec. This is the last one we're going to do. So then you do it for the third time. You then use, this is the number you use. So I'm just going to, again, I'll tell you because you can see how tedious this would be. F of 1.4167 is going to give you 0.0069. F prime of that number is going to give you 2.833. So then, when you put that into this equation, it's 1.4167 minus 0.0069 divided by 2.833, and that will spit out 1.41426. So what'll happen is the numbers will start to repeat. The decimals that repeat will start to get longer. So we got This is 1.5, and then we got 1.4167. Now we got 1.41426. If you did it again, it'd be like 1.4142, blah, blah, whatever. Right? The amount that repeats starts to get longer. So when you get like 3 or 4 decimals, it depends how accurate you want to be. That's when you stop. Okay? So we're going to stop here. Can you tell me what the actual x-intercept is? How would you solve that? Yeah, because if you're going to actually solve it, you would go 0 is equal to x squared minus 2. 2 is equal to x squared. So you'd root the 2, and you would get 1.4142. You do it until these numbers start to repeat enough to satisfy whatever method you're doing. So if I was asking you on a test or something, I would say go until the first 3 decimals repeat. So I would say you just stop there. Okay. Or first 2 decimals or whatever. But you can see, look how close you got. The actual answer is 1.41421. We got 1.4142 and then 6. That's only after 3. If you go more, you're going to get more and more. You're going to get closer and closer to the actual number.
So this only helps us with x-intercepts?
Well, it's solving equations, right? If I said solve, I mean, it doesn't matter. You know how to solve this. Make that a 10, a 3, now put sine x. Solve that. So what you would do is you'd pull that over. You do the same thing you do for trig or for quadratics. You just pull everything to one side. Now, this equation is saying, where does it equal 0? I.e., what are the x-intercepts? But I don't know how to solve that. That's a gong show. But you could use this method to do it, and it would solve it. All right? And that's essentially, if you put that into Desmos, it'll spit out the x-intercept. That's all Desmos is doing. It's just using this algorithm, and it's doing this really, really fast to spit out the answer. Now, it doesn't always work. There's a couple cases where it doesn't work. Okay? I'm not going to ask you to go through this on a test because it's tedious and boring. But it's a useful tool to know. So, I'll just say the system fails if your initial guess has a slope of 0. So if your initial guess has a slope of 0, it means you have something like this. It's easy to look at it visually. If this is my initial guess, x1, all right, and you try to do the tangent line, well, with the slope of 0, is there ever going to hit the x-axis? No. So if your initial slope is 0 at your initial guess, you have to pick another point. That's not going to work because the whole point is to make this hit the x-intercept and then use that to generate the next one. But if it's never going to hit, then it doesn't make any sense. Okay? And the other one is when so if you pick your initial guess too far away from the x-intercept, what can happen is the graph will just start spinning it way far out of control. So visually, if I pick a point here, there's my guess. Well, I draw a tangent line at that point. I can't draw a tangent line. and I draw a tangent line. It's way out here.
Wait, can you do this without having a graph?
Yeah, that's what the formula is.
Well, then how do you like accurately pick
We
like a guess?
use intermediate value theorem to start guessing where is it above, where is it below. That's how you would actually do it. I would give you an interval.
Oh, there's too many.
All right. So you can see if I pick it way too far out there, my first point's going to be here. And then I do a tangent line again. Gosh. And then my next tangent line is here. But by then the graph is, I don't know, here. And then I draw a tangent line. Oh my gosh. Now it's going even farther away. So instead of getting closer to our x-intercept, we're going further and further away. Okay? So if your initial guess is too far away, it doesn't make any sense. That's where you would use the intermediate value theorem, but I would probably just give you a domain range of what to do.
Why would you draw this?
You don't draw it.
No, like why would you draw this when you can just plug in zero? That's not
You don't do that. Like, you're not going to do this now because we have all the tools, right? I mean, you might use it to prove something way down the road, but you're not going to do this, right? This is what they did back when. And then this is essentially the algorithm that computers use to solve it.
They don't know that x equals. They didn't know that y equals zero.
Yeah, but if I say, like, if you go back to this, how do you solve that? How do you solve this? How do you solve this? How do you make that equal 0? You can't factor it, right? Because it's got like complex functions. You can't. That's what it's used for, is complex functions, not for quadratics and things like that.
And it doesn't work if it's not continuous, right?
If it's not what?
Like not continuous.
Yeah, it has to be continuous, because otherwise the derivative could blow up somewhere. All right, we're just going to stop there. Tomorrow we're going to do linear approximation, which is fairly straightforward, something similar to this. It's actually pretty cool. And then your midterm's Friday. Midterm is Friday. Friday. And it's not, don't be scared about the midterm. Do not be scared about the midterm. It's mostly multiple choice with 2 short answer questions. What? Limits, derivatives, and curve sketching. It's all derivatives, basically. And then we're on to chapter 4, which is the reverse process of all this. The midterm is usually well done in this class.
Okay, I have another question. When are you going to post it? Like, how many questions are there going to be? How many marks is this question going to be?
Probably Wednesday or something.
Sorry?
Wednesday or something. Like on the midterm, you mean? Yeah, probably Wednesday. I just have to tweak it. It's almost done, but.
Okay. And you will post exercise practice for this?
And then, so tomorrow we're just going to do linear approximation, and then it's review Wednesday, review Thursday, midterm Friday. That's all we're doing this week. And then chapter 4 starts next week. Okay? Don't be freaked out about the midterm. It's straightforward. Problems. Related. Oh, optimization? I haven't finished the midterm yet, so I can't tell you that. That'll be the bonus question. Maybe that'll be the question. Optimize your mark for this class. Go. What? You're gonna be sick on Friday? This midterm is not like your grade 12 midterm. This counts for 10% of your mark. Does anybody read the outlines I give? What? Final exam is either 20 or 100. Yeah, if you beat your overall mark, then that's your mark.
现在就看我命用不用。
来吧，失败就点。
救命！失败就点，真的。我把他知道他。
失败就点，失败就点。哎，咱假装看不见对吧？咱自欺欺人。
赢了，操你妈！
Don't worry about the midterm.
And you just hit 10% to win.
It is easy. I don't understand pages. It's like, well, look at this. I can test 3 chapters. Right? I can't test like a lot of depth in chapters. Or like, do you know how to do derivative? Do you know how to do limit? Do you know how to curve sketch? Like it's the big ideas. Right?
I don't know how to.